you'll see that by going down the correct path of on the other side, okay. All right, so I just cheated, looked up this equation, and I'm going to reconcile it with the work we've done so far. So this is, now, you'll see this a different way. So Q, if you remember the second law of thermodynamics, is usually the symbol for heat. In this case, these authors have used Q for the heat transfer rate. So typically what you'd see is this Q with a little dot over it, because see the T for time in the denominator? That's the same as the dot. So this thing right here is the heat transfer power equation, written as so. We can rewrite it in our own little funny way that we started on, and I'll show you exactly how. But tell me what the across variable is here. Specific heat, it's not the across variable. The specific heat's just kind of there as a little accounting system. We can kind of assume that that's just the number one. That's just there to make sure the units work out. It is, yeah. In this case, that's exactly what it is. The delta T is the across variable, because you get cold on one side, hot on the other. So the through variable is roughly what we wrote a second ago. It's roughly what we wrote a second ago. The through variable, we wrote it as the volumetric flow rate, which is valid. The way it's written here, it's the mass flow rate. You see that? We're kind of trying to jam mass into that across variable, but the way it's written here, it does actually belong in the through variable. So let's just back up one quick second. We weren't wrong, but I'm gonna backpedal just a tad here, because I think you can appreciate that where we were going, eventually we would have worked density in there to get mass, but the simpler way to write it, and I'll just go ahead and erase my little V dot. And I think you could see that if we were to, well, let's just write one more little thing here. This will make us all feel a lot better. Density equals mass times volume. And another way to write that is volume. Oh gosh, why did I write that? Layton, somebody slow me down here. Mass divided by volume, thank you. Saw Dustin checking his notes, make sure he was in the correct universe, not in some. So we'll rewrite that as volume equals mass over density. Good? Good. Now, we're going to take the time derivative of both sides, and we can write that the volumetric flow rate is equal to the mass flow rate divided by density. So I just divided both sides by time. So what we can do is just replace the, I'm going to replace the V dot with the M dot. Well, I mean, M dot is really, let's just rewrite it this way. M dot, actually, no, I don't have to rewrite the dang thing at all. I can just write rho V dot, because we know the density of air, 1.23, etc. We can measure the volumetric flow rate, because we know the area and we know the velocity. So that chunk right there is the through variable. That's the m dot from this equation. The only thing we need to do to nail it now is put C sub p up here, and then delta t. That makes everything work out. So where I was going with this, guys, I don't know if you're going in a similar place. I started off with the ideal gas law, IGL, to really get at what the fundamental units of temperature were. I think you could see that eventually I would have worked my way around to this, but it wouldn't have been pretty. So I think we can see, and again, it's not that good looking either. I think you can agree that the mechanical thermal equation is not as pretty as the electrical or the mechanical linear, the mechanical rotational, because the through variable is this little chunk right here, and the across variable is this guy. So that should be pretty clear, because what you can see now is you're going to know that delta t, because that delta t, well, what the heck is delta t? Delta t, from our power equation, delta t equals the temperature in the garage minus the temperature in the system, or vice versa. I mean, obviously, you can't have a negative temperature. There's no such thing as negative temperature, but you can see that the absolute value of that delta t is what's going to matter. And whether you're talking, and so what you'll know from that is how much heat is flowing from the system into the garage, or another way of thinking about it is like how much energy the garage is stealing from the system. It all has to balance out. You still have to go back to that first law of thermodynamics. You're not making energy anymore. You're just pushing it around. Okay. Okay. So now we've gone to all that trouble to come up with the power equation for the solar thermal system. There it is, right there. So when you're sitting down, scratching your head, how much power can my system make? Well, there it is, right there. So you can, right away, you can tell off the bat, the hotter the system is, the more powerful it is. If the air were more dense somehow, and this gets back to thinking about, okay, so how might you make the air more dense?
Humidity.
It would be humidity, yeah. And I think we all know this. If it's humid and cold, you're losing heat more quickly. And another way, obviously, is to push more mass through the thing, right? Just make the fan blow harder. But now, where's the limit there? I mean, why not say let's just blow it infinitely fast and we'll?
Then it loses efficiency because it's not capturing the heat when it moves.
Yeah, if you just blow it through so quick, there's not enough time. The air does not spend enough time in the system to actually gather any heat. It's just flying through there. So there's a balance point there where if you start dumping too much energy into making V dot, into making the volumetric flow rate too large, then you're being counterproductive. So somewhere in that middle, and I'm not going to, like in your theory section, I'm not going to say, okay, Ryan, you got to sit down and tell me exactly what the optimal blah, blah, blah. That's beyond the scope of the course. But I think you can appreciate that there's some subtleties there in terms of maximizing the performance of this system. You can't do anything about C sub P. So, okay. Now, in the time we have left here, let's just go through a numerical example and estimate what we think the power of this system might be. So I'm going to use the Wonder Woman magic lasso. Copy? You guys ever do that luminosity stuff at all? You ever try that?
Keep your brain sharp.
Yeah. Yeah,
It's a good word for me.
does it, yeah?
Yeah, like that.
I tried the other day, man, I was like 90-something percentile on one, but then like 50 on another, man. I'm like, God, I don't know, my brain is slipping. It was making, trains go to different tracks. You had to like switch gears on this maze. Anyway, I'm thinking
I
like,
just find some of those things to become increasingly tedious.
that's the point. The point was to see how well you can deal with tedium.
Well, doing a level 4 Sudoku does the same thing, so you have to guess and check.
Yeah, yeah.
Then remember everyone, once you mess up that one number, you gotta go all the way back through.
All right, guys, so let's just do a little back of the envelope calculation and see what we might expect for this system, right? Because you're going to be out in the field, you want to design your own system. Now, P equals, so C sub P, what does C sub P equal? We already know, equals 1 kilojoule per kilogram Kelvin. Nice. What's a reasonable delta T for this guy going to be? So we got delta T equals T system minus T garage.
20 degrees, 9 degrees?
I think it's gonna be a couple degrees.
So when we ran it on my office,
Before I got forced to
before
look it down.
before it was condemned, thank you, we were seeing 220, sometimes 240 Fahrenheit coming out of that bad boy. Like if design, you could boil water with it. So I'm just gonna throw out 100 degrees Celsius.
So it's in Celsius. Oh.
Well, because really what we're concerned with is the delta T. We don't need the absolute temperature. And a delta T in Celsius is the same as a delta T in Kelvin. Good, okay. And then, so it's 100 degrees inside the system. Temperature in the garage,
Let's call it 60.
60 Celsius is still pretty
Oh,
hot.
no,
Yeah,
okay.
yeah.
What was the temperature in the ground?
Well, like, I don't know, we're kind of thinking like Montana winter morning here.
So that'd be like, it's
You know, I mean, freezing, let's just say it's freezing in there. That's 0.
Maybe like 20 degrees?
Yeah, it might be, let's just say it's 10. Let's just give it 10. It's not quite freezing. You're not going to walk in your garage and there's like ice cubes sitting around. So let's just say it's 10. So minus 10. So we might need 100, might be 10 in there. Now, density, and I'll put a C here. Density equals, do you remember off the top of your head, Corey? You've been doing these lately.
1.2 kilograms per cubic meter.
You only got 2 sig digs for me? 1.2.
0.204.
We'll leave it at 1.2. We'll leave it at 1.2. 1.2, kilograms per cubic meter. Right, thanks, yeah. Per cubic meter. And then the volumetric flow rate, we're going to have to get a little bit creative with this guy, but that's going to equal the area times the velocity. And now the area, let's just run through this. Area equals pi r squared, and the radius equals, on this guy it's a 4-inch duct, so that's 2 inches equals, let's just pop that into meters. Inches to meters, 0.254. So calculator, 2 times 0.0254 equals 5.0508 equals 0.0508 meters, right? Equals pi times 0.0508 squared. So times 0.0508 times 3.14 equals, I guess it's about 1/10 of a square meter. I guess I believe that. It's not, no, it's 100th of a square meter. Yeah, I guess I believe that. It's not very big. I'm just going to call it 100th. Equals 0.01 square meters, meter squared. Okay, so 0.01 meters squared. Now we need a velocity going through this thing. So, just imagine sticking your hand in front of the system. It's going to be somewhere between 1 and 2 meters per second. Certainly not just imagine, the chunk of air coming out of the thing. Okay, now it's out in the room. It's going to take it about a second to get from the system out into the room. So maybe 2, maybe 1. We're getting an approximation here. You'd have to. So this would be a little theory. Remember, like I said, a little theory. This is all you need for a little theory. Velocity. I'm going to throw that around. Let's just use 2. 2 meters per second. Now, if you were
Is that square meters?
velocity is just meters per second, because now you can see what we're going to end up with. We've got area times velocity. Area is in meters squared. Velocity is in meters per second. We multiply those together, we get cubic meters per second, which is exactly what we want. We wanted cubic meters per second for the volumetric fluid. Yeah, good question. So now let's just kind of plug and chug from here to try to see what kind of power we're going to get out of this guy. What's missing, though? Something seems like it's missing. Mass? No, I guess not. Delta T. Yeah. Let me think about this guy. There's a few more, because you'll notice nowhere in this equation did we have the size of the panel, did we? So this is where we can get into this design a little bit. Let's see how powerful it is, and then the question is whether the sun is actually cooking it this much or not, right? You're gonna have to make your panel large, like at least as large as this, because otherwise you get this tiny little panel. There's not enough solar power hitting it either. So we need the solar thermal power equation. We also need our just 1,000 watts per square meter. Multiply that by the square meters. That's the solar power equation. That's pretty simple. Okay, so let's just run through this. So equals, and I'm going to skip the units because I know we were very careful. So power equals 1 times 90 times 1.2 times 0.01 times 2. Double check. Heat capacity is 1 kilogram per kilojoule per Kelvin. 90 delta C or delta K, same thing. 1.2, that's in kilograms per cubic meter. Everything's SI. 0.01, that's in square meters. And 2, that's in meters per second. It's all over but the crying. All right, so let's just run it. 90 times 1.2 times 0.01 times 2 equals. Yeah, here's where I'm crying. That's pretty low.
Is that?
2.16.
You have to change kilojoules to joules for that?
Yes, my man, thank you. I'm not crying anymore. I only cried for like 2 seconds there. I thought the same thing. Like, what's wrong with that? Is that 1.26 watts? No,
It's kilowatts.
it's kilowatts.
But Celsius can stay Celsius.
Celsius can stay Celsius, doesn't have to turn into Kelvin. 1 degree Celsius equals 1 degree Kelvin when we're talking differences. There's no change there. Yeah, I think here's where it came in, right here. Kilojoules, bam. Kilojoules turns into kilowatts, so it's 2.16 kilowatts. Thank you. Perfect. So, now, in the morning, when the sun just barely pops up and your system is not pointing at the sun, are you going to be able to make 2 kilowatts from from the radiation?
Negative.
Probably not. Now, make the thing is really super big, maybe, but now your fan isn't powerful enough to run the thing. So what I suggest you try to do over at Nikki's house is cheat that thing towards the east a little bit. Because typically what you want to do is heat it up in the morning before you go out to the garage a little bit. And by the end of the day, it's probably hot enough. You don't want it any hotter. So you cheat it towards the east a little. Yeah, you know, I don't need you to build the sophisticated thermal tracking system like we had over there at the hydrogen fueling station, but I think you get the point. So guys, was that helpful? Just, you know, kind of run through the theory. What I hope I did for you here was put everything in context. I think it's important to go back and just look at all of these different systems. You know your electrical, cold, we reviewed the mechanical linear, we reviewed the mechanical rotational, kind of struggled our way through the mechanical thermal, but they're all power equations. That's the beauty of this stuff. They're all power equations. Did a little dimensional analysis that helped us through, went back to the ideal gas law, looked through the definition of temperature. I hope that was not too deep of a rabbit hole, but something to scratch your head about when you're going to sleep at night. And then actually came up with a reasonable thing. So 2 kilowatts. Now, next thing you might try doing is compare that to an electric space heater. And then decide how much money it would take to run your electric space heater at, you know, what is it?
13 cents.
13 cents, so, yeah, 13 cents per kilowatt hour, et cetera, and, you know, and then you could get a payback period for this guy. You know, when couple $100 device, whatever it happens to be, run this thing for 10 hours, there's $13. Run it for 100 hours, there's $130. So, you know, run it for a couple $100 hours, it's paid for itself. Got to know what, you know, and then the next question is, where's your electricity come from to run it? Well,
But you have to count how much electricity your fans using, so
yeah,
seemingly get more complex.
yeah, it would. And you would subtract that too. But, you know, and this is the way we design the system. We do have a little PV on the top of it. You know, if properly designed, your PV is the only thing running the fan. So you're not paying for electricity. I mean, you put the capital cost into the PV panel, but you're not paying continuously to run the fan. It's coming directly from primary solar energy instead. So anyway, that's kind of your next step in terms of does it pay for your customer? All right, battery's dying. It's 3:36. We're out over time a little bit. Any other questions? I'm going to wait and see how everyone does on quiz 2. Take quiz 3 also, please.
Just do overzealous on quiz.
Do quiz 3 also. I'll get them graded, and we'll cover quiz 2 and quiz 3. I'm thinking by the end of the semester, probably get you one more quiz, and then just a final. And the final's gonna cover some problems like the stuff we did today. Some more things out of the book. It'll be open book. It'll be, similar to what you see in 101. Okay, turn to concentrated solar systems and tell me what the heck's going on there. We'll give you some warning on the final, but that's kind of it. That's it for the class. So next week, shoot me your project proposal, please. It's with the items I mentioned, and then we'll go over quiz 2 and 3. The idea being there'll be one more quiz, your project, and then a final. Done. Okay, thanks.
So we're meeting at Nikki's on there?
Yeah, I put Tim in charge, and I think just get yourself to Nikki, ride your bike, hitchhike, carpool, however you do it, I don't know.
Where does she live?
She's at 320 Easy Street, so out on Broadway. And I'd like somebody to do a little photo documentation, just a little nice window dressing for the course website. Maybe we pop something up on our energy blog, good PR.
Well, yeah, I'll take my camera.
Do you wanna let me know where that tracking thing?
Solar Pathfinder?
Solar
It's in
Pathfinder.
Brian Kern's office. Do you have time to grab it from
Where
him
is
today?
that?
He's in the bowels of facilities. No, you've been to facilities.
I have.
Well, it's not that
I don't have time
stinky.
to get it today.
Uh,
I've got one or two right now.
Could you get it in the morning?
Something to do. Yeah. I can do it in the
Okay.
morning.
I'll tell Kearns you're gonna grab it from him in the morning on the way to Nikki's.
So
Can you text me or email me what room number
Yes,
it is? or
yes,
something like that?
yeah. Thanks, Corey.
Yep.
I'm just gonna sit here and ask you a couple questions.
Okay.